So here's a question. Here's a question. I talked about IQ earlier. We just looked at a graph of 100 randomly selected IQs. You guys correctly pegged the average as 100, because it is. The standard deviation is about 15. Now, you might not have gotten that value off of this curve, but could you have approximated that value off of this curve? Could you have guesstimated that the standard deviation was about 15? Yeah. Knowing that, tell me how, Monica, go.
Because if the average is at 100, the one, it looks like it's to like 125 or something. So
what are you using in your head right now? It's an old idea. We haven't used it in a bit because of
putting the fences.
The fences at where, Carly? 95%. We haven't used this in a bit. Now the reason we haven't is because using the binomial distribution, very often those are not bell-shaped, those are skewed. Those are skewed, very often, very, very often. We have a fix for that next week, I promise you right now. But, right now, this doesn't look skewed, highly skewed at all. So if you think the average is here, and you kind of pop out to where roughly 95% of the data is, if you think about that, that's roughly 30 data points down and 30 data points up. That's 2 standard deviations is 30. That means 1 is about 15. Does that kind of make sense? Hopefully that makes sense. Good. Very good, very good, very good. So let's look at this question again. Adult IQ is about bell-shaped. Normally distributed is stat speak for bell-shaped. Let's put that on the board, make sure you guys take it away. Normally distributed is just a fancy term for bell-shaped data. Normally distributed. We usually call it bell-shaped. I wonder where bell came from, that phrase, bell. When's the first time you guys heard that? Oh, sorry.
Looks like a bell.
Well, it does, but I wonder why a bell versus... See, I can't think of anything else because I see a bell now, because I've heard it so... Oh, Vivek, what do you got? You sure? I wonder, like now I can't think of anything else except the bell, because that's what I've heard.
Versus a mountain or a hill.
Versus a mountain or a hill shape, mound shape. Looks like an anthill shaped data, I don't know. This is kind of crap I think about. When you have normally distributed or bell-shaped data, you have to also know its mean and its standard deviation. And keeping with our practice that we've been keeping with the practice we've been keeping with, I want to keep calling those mu and sigma. I want to keep calling those mu for average and little sigma for its standard deviation because we have the population essentially. This is a distribution just like a binomial. So we can get away with calling it the average mu and the population little sigma. I know technically speaking we can't because you don't actually have your entire population, but everything we're going to be looking at has been sampled so many hundreds of thousands of times, you can essentially act as though it was the perfect average and the perfect standard deviation. Does that make sense? So in other words, when you see mu and you see sigma for the average and the population standard deviation, realize there are margins of error on them, but they're so small as to be 0. So you can call them mu and sigma, it makes life easy. So very often, actually all the time, when you deal with bell-shaped data like this, I posted your guys out of class, your second exams last weekend, you probably got the email about them. One of the questions on there is about the Tower of Terror at Universal Studios. It's all about this. It's trying to figure out what percentage of, I think it's 6-year-old kids, because I'm using Max as sorry I keep using Max in class, it's so easy to. What percentage of 6-year-old kids can ride the Tower of Terror based on the parameters of 6-year-old kids' heights? Yeah, it's super fun. It's super, super fun. Now, in order to get that, you first have to Google the Tower of Terror height restriction, number 1. I give you the link for it, so that's not actually have to Google it, you have to click on a link. Then you have to read a pediatrician's growth chart and figure out what the average standard deviations are for a 6-year-old. And I teach you how to do that on the exam proper. So in other words, you have to figure these things out for 6-year-olds. You know they're going to be bell-shaped. Why? Because we just looked at data of women that are bell-shaped, and all people tend to be bell-shaped when you graph them. Most of them are around the average. There are a few very tall people, few not so tall people. Generally, they're mostly in the middle. Why? I don't know. We just are. I'm guessing it's a function of how we grow up in genetics and things like that. So when you have bell-shaped data, you have to talk about its average and its standard deviation while you're talking about the bell shape. So the bell shape, okay, first question is, where is it centered? The bell can slide left to right. I mentioned that wait lists at COCC were bell-shaped. Sometimes they used to average 7, sometimes 15, sometimes as low as 3. That means the bells were sliding back and forth depending on the term. This way, this way, this way. The next question is, how tight are those bells? Are they big, wide bells with big sigmas, or are they really, really tall, skinny bells with tight sigmas? More on that next week, too. You can control that via sample sizes.
You can control that?
You can control that in sampling via sample sizes. Okay. You can actually control the variability. You can't control sigma, but you can control the variability in your sample via sample size. Thank you for catching that. Very good, Pat. It's called the central limit theorem. It's our last topic of the term. We'll get into that next time. Now, once you know this, I want to see how we can answer a question like this. What percentage of adults are dull normal? How many of you guys have ever called somebody an idiot? Yes, Cassidy's hand shoots right up, thank you. You're like, how about an imbecile? How about a moron? Oh, more hands each time. Moron. Where do these terms come from? Big brothers. Mental health journals from the 50s and 60s. Those were IQ cutoffs. I wish I was kidding. These were terms that did not used to be disparaging in the common conversation like they are now. You never call your friend an idiot in 1942. Because first of all, the term idiot wasn't around. But secondly, when the term idiot was around, it became an IQ cutoff. It was somebody with an IQ, say, and I don't remember exactly, you can Google it and find out. An IQ below, say, 70 was an idiot. Below 65 was an imbecile. Below 60 was a moron.
So it was actual medical.
It was right, it was actually an IQ psychological phrase. Yes, exactly, Patty. Yes. But now we've changed it because we're more PC. Now it's dull normal. Dull normal is an IQ between 80 and 90. So what do you think? What do you think?
What are you, like, not lively at parties, or, you know?
No, it's an IQ. You're not IQ eating at parties. Well, you're dull normal, which means you have an IQ between 80 and 90. So think about that. You can see why it's below average, right? You can see why it's below average, because average is 100. But the question is, if you had to tell me what percent of the population is between 80 and 90, how are you going to do this? I mean, one way you could do it, let me pause this for a second. We'll come back to this question momentarily. But one way you could do it is you could try to attack it like we did with the binomial. Yes, we could. Yes, we could. Let me back this out and restart it. We could, if we